YouTube video for chapter 16, which is all about winter weather. For those of you who are taking this class during the summer as a distance course, you're probably taking this class and seeing this video during a time of the year when it's really, really hot, and maybe winter weather seems really appealing to you given what the weather is like outside. If you are taking this class face-to-face with me, you may be watching this video at the very end of fall semester when it's actually cold enough for us to be getting winter weather here in Northwest Ohio. So either way, whether you're looking forward to a little cold weather or you're actually in it and it's about to snow, hopefully you'll enjoy this chapter. I am a big winter weather enthusiast, and so this is probably one of my favorite chapters in the entire course. And speaking of the course, this is the last video for Geography 2130. So regardless of whether you're taking this class as a distance class or in my face-to-face classroom on campus, this is the last chapter and the final exam is coming up very quickly. So I hope you've enjoyed the class, I hope you enjoyed this video, and I hope that all of these videos have helped you to succeed in our classroom. So let's get started with the slideshow. And here we go. So what I want to do first is just start with a schematic of a mature or early occluding mid-latitude cyclone. And this is obviously just a drawing with a low that's centered over southeast Nebraska with a short occlusion into Missouri, and then the cold and the warm fronts. Now the reason I want to show this is because unlike summer phenomena, where we're really basically dealing with rain and perhaps on the off chance hail, with big winter storms, we typically see all kinds of precipitation types. So we typically get rain right along the warm front and the cold front, sleet, freezing rain, and then obviously snow with a winter storm. So we do get a lot of precipitation types. I'm going to talk about these precipitation types in a moment. Just to put this in context with our conveyor belts that we talked about in earlier chapters, here is the warm conveyor belt, which basically extends to the east of the cold front and all the way to the north of the warm front, where we have our overrunning precipitation. And then we have our band of heavy snow, which falls basically beneath the cold conveyor belt on the northwest quadrant of the low. So here's our cold conveyor belt. And then our dry conveyor belt, remember this is dry troposphere or tropopause level air, which is sinking in beneath the low. In terms of beneath, it's basically to the west and south of the low, and it's tucking in to the low basically from the south and the west. So here is our dry conveyor belt. But when it comes to interesting precipitation types, the precipitation types that we either love or hate in terms of frozen, snow, or freezing, sleet and freezing rain precipitation, these basically all occur within the warm sector of the extratropical cyclone. So typically when we get freezing or frozen precipitation, particularly sleet and freezing rain, what we see is that we're actually dealing with an overrunning situation. I'll just go back again so you can see where the sleet and the freezing rain is. It's to the north of the warm front. This is where our overrunning is occurring, and this is associated with warm conveyor belt air that is intersecting the warm front and is being forced to rise up and over the decaying or the stale cold air to the north of the warm front. And so what we see, and we've talked about this before early on, probably in chapter 6, is what we see with overrunning is that warm air to the south of the warm front is forced to glide up and over the stale cold air that's to the north of the warm front. And so what we see is that the warm air is actually elevated to the north of the warm front. So the warm front will be right here at the surface where you can see our red and our blue are meeting at this point. And so what happens is to the north of the warm front, the warm air is forced to rise or glide up and over the retreating stale cold air, and this is overrunning. So what you see is that while the temperatures at the surface may remain below 32 degrees Fahrenheit or 0 degrees Celsius, the overrunning air that basically is gliding up and over this retreating cold air can have a temperature below 0 degrees Celsius. Now, you can see that the overrunning air gets shallower and shallower in terms of temperatures that are above 32 degrees Fahrenheit. But the reality is that the overrunning can actually extend well to the north of the warm front. But because of adiabatic cooling, typically dry adiabatic cooling until we get our first clouds, and then moist adiabatic cooling. But what happens is, as this overrunning air glides up and over the cold air, it expands and it cools, and even the overrunning air will eventually cool to a temperature below 32 degrees Fahrenheit or 0 degrees Celsius. So if we get far enough to the north of the warm front, even though we have overrunning air at this high altitude, it is cooled via expansion to a temperature below 32 degrees Fahrenheit. So what you see here in terms of precipitation types, if we basically move from south to north, is that if we're really far to the north of the warm front, the overrunning air will have cooled to a temperature below 32 degrees Fahrenheit. Precipitation that falls from the clouds will fall through a vertical profile where the temperature all the way down to the surface is below 32 degrees Fahrenheit. We'll get no melting, and it simply snows. Now, as we get closer to the warm front, what you'll see is that we get a bit of a nose of warm air above 32 degrees Fahrenheit against this overrunning air. And so what happens is snow will fall into this shallow, cold air, it will melt, and then form rain. But as this rain falls beneath this warm tongue, it will fall back into air where the temperature is below 32 degrees Fahrenheit. And because this layer is really thick, this liquid water will have sufficient time to freeze. Note I'm saying freezing here, which is the phase change from liquid to solid, versus deposition, which is the phase change from vapor to solid. So freezing occurs beneath this warm tongue of air, and we get sleet. Now, as you move closer and closer to the warm front, what you see is that the depth of the warm layer increases, the depth of the cold layer beneath it decreases, and so while we get melting still in this warm layer, when the rain falls into the cold layer beneath this overrunning air, it doesn't have sufficient time to freeze before it reaches the surface, and so what happens is liquid hits the surface and then it freezes on contact, and this is freezing rain. Note that even though liquid is falling in this cold air above the surface, it's shallow, but the surfaces will have a temperature below 32 degrees, so your car, telephone wires, trees, all of this stuff will end up accumulating ice that freezes on contact, and this is freezing rain. And then obviously, when you get to the warm front itself, then what you see is that the temperature is above 32 degrees all the way down to the surface once the snow falls into the overrunning air, and we simply get plain rain. So again, if you take a look at this previous slide, you can see the scenario from snow to sleet to freezing rain to rain. So just put these two slides together, and that will help you to understand how it is we get the various precipitation types. Okay, and again, I just indicate that this is just overrunning within the warm conveyor belt. This is all warm conveyor belt air. It's all overrunning air. It's just simply the fact that as this overrunning air rises, it will expand and cool. Eventually, it will fall to a temperature below 32 degrees Fahrenheit. So just to remind you what sleet looks like, these are ice pellets. Very different than hail, which forms very, very large chunks of ice during the warm season in thunderstorms, and that's as a result of ice being thrown up into the thunderstorm over and over again by very powerful updrafts. In the case of sleet, this is just simply a droplet of rain that freezes beneath the warm conveyor belt into an ice pellet. And so sleet is always small. It's always basically the size of a grain of sand. And so here's just an example of a temperature profile where you have snow falling out of a cloud, falling into a relatively shallow layer of overrunning air where it melts, and then falling into a deep layer of sub-32 degree air beneath it where it freezes into an ice pellet. Freezing rain, on the other hand, this is what it looks like after freezing rain actually freezes on contact with a small branch of a tree, and you can see it's actually quite beautiful, but you can see how it is that it adheres to all the shapes of this branch. Now obviously, while it's beautiful on a branch, it's not so beautiful if the trees fall on power lines or the power lines come down as a result of the weight of the ice and you destroy property. And also, obviously, it's not great if it's on the road and you can't drive because the road is a sheet of ice. Here is what the vertical temperature profile looks like when we get freezing rain. So again, what you have is a situation where snow falls into a layer of air that is warmer than 32 degrees Fahrenheit. This layer is now thicker. We're closer to the warm front. And still, what happens after this snow melts to form rain in this warm layer is it falls into a sub-freezing layer of air above the surface. However, because the layer above the surface is fairly shallow, where the temperature is below 32 degrees Fahrenheit, what happens is that the rain reaches the surface as liquid. It does not freeze into an ice pellet or sleet, and so we simply get this freezing rain, which then freezes upon contact with all of these surfaces that have temperatures below 32 degrees Fahrenheit. And as we know, freezing rain can be extremely destructive. This is a picture of some high tension power lines in southern Quebec near Montreal in January of 1998. This is actually a pretty famous ice storm that occurred right after the first of the year. This ice storm went on for 3 or 4 days, and basically what happened was overrunning north of the stationary front occurred. And again, it was over a period of 3 or 4 days. And what happened was the ice accumulated, in some cases, to 2 or 3 inches thick, which just puts an immense amount of weight and strain on these wires and stands. And you can see they just crumpled to the ground. So here's the setup, and this is for the event that occurred between January 6th and 9th of 1998. So we have subtropical high pressure off the east coast of the U.S., and the clockwise and hour directed circulation around it pumped up maritime tropical air and along the east coast. And then this front right here should actually be a stationary front because it was for a period of days. But we have the stationary front located right here, extending from low pressure along the Ohio River. This warm, humid air glided up and over the cold air to the north of the front, and instead of it retreating, it just basically held firm for a period of 3 or 4 days. And then as we got our overrunning air in this warm conveyor belt gliding up and over the cold air to the north, we got clouds and precipitation, and relatively close to the warm front in southern Quebec and upstate New York, Vermont, New Hampshire, and Maine, we just had a period, again, of 3 or 4 days of just freezing rain, which again was incredibly destructive. Millions of people lost their power, some of them for weeks, obviously in January. So it was a very, very dangerous situation. Here is a vertical temperature profile just for the lowest 3,000 meters or so of the atmosphere over a location in southern Quebec. And you can see that the surface temperatures were below 0 Celsius, so below 32 degrees Fahrenheit, until we got to about maybe 950 meters above sea level. So basically, you're talking about a location that's about 875 to 900 millibars, and then the temperature went above freezing and stayed there all the way through 2,000 meters. And so this is about from 875 probably till below 800 millibars. So this is a really thick layer. And you can see that we got up to about 3 degrees Celsius, which is probably about 37, 38 degrees Fahrenheit, more than enough to melt the snow that fell into this layer. So again, a couple of days of this and just very, very destructive. Now let's move on to storm tracks that impact us here in the United States when it comes to winter storms. So unlike the past couple of chapters that we've been covering in our class, so this would be chapters 9 and 14 and 15, where we talked about convection and thunderstorms. We're talking about now really large, organized mid-latitude cyclones. And although short waves do play a role, we're not going to really talk about short waves in this chapter. Just know that short waves can really amplify these patterns that I'm showing in this slide. But typically in the United States, during the cold season, we either have zonal flow or highly meridional flow. And we get our big winter storms when we have highly meridional flow because we tend to have really well-defined vortexes. We also tend to have pretty well-defined jet streams with jet streaks in them. And so kind of everything comes together to lead to the divergence of mass through a large thickness of the tropospheric column. And so that leads to strong low pressure at the surface. So typically what we see in the United States is that we either have a west coast ridge and an east coast trough, or the opposite, a west coast trough and an east coast ridge. So if we take a look at our first example with a ridge in the west and a trough in the east, this is typically when we get our storminess here in the eastern part of the United States, not surprising. So you can imagine that with a really high amplitude ridge in the western part of the country, we're going to end up with convergence, basically somewhere between the ridge and the trough, and with the trough and our vortmax basically somewhere in the base of the trough. As air flows through this trough pattern, we're going to get decreasing vorticity, mass removal, and divergence through the column, and low pressure somewhere located over here, in this case just off the east coast. In the case of our cold west, warm east, better words, trough in the west and ridge in the east, we now see our vortmax in the west, in this case depicted over the southern tip of Nevada, our vortmin in the east, located over far northern Maine, and basically what happens is we get our upper level divergence, mass removal from the column over the middle part of the country, and this is where we tend to get our lows. Now I want to just point out that if you just take a look at where Ohio is, given these kind of predominant general wave patterns, you can see that Ohio is really pretty far from low pressure in both of these examples. And in fact, here in Northwest Ohio, it turns out that it's pretty darn difficult to get a heavy snowfall because the climatological patterns don't really favor us getting into the northwest quadrant of surface low pressure. So basically here in Northwest Ohio, it's not a great situation if you like snow. And I do like snow, so it's kind of depressing at times here in the winter for me. So if we take a look at some of the winter storm tracks that we see over the United States, and this is straight from the text basically gives you, let me see, 2, 4, 6, 7 different predominant storm tracks that impact the United States, but primarily the central and eastern United States. And you can see that most of these storm tracks kind of miss Ohio. Now, I just want you, I'm not going to go back and do this, but if you go back to our very first slide in the presentation that shows you our classic mid-latitude cyclone and where the precipitation types are located, you can see that in order to get the heavy snow, you kind of have to be in the northwest quadrant of the low. And really, you need to be within maybe 200 miles of the low center or a little bit more. And that's it. So if you take a look at all of these storm tracks, you can see that really only one storm track really puts Northwest Ohio in the running to get heavy snow, and everything else kind of misses us. So Texas, this particular storm track is the storm track that we look for here in Northwest Ohio to get heavy snow. And really, ideally for Bowling Green, what you're looking for really is a track that kind of takes the low, maybe from Cincinnati through Columbus to just east of Cleveland. That is a storm track that is ideal during the wintertime to put down a strip of heavy snow over Northwest Ohio. We can also get snow here in Northwest Ohio with Alberta clippers. These are lows that form over, obviously, the province of Alberta in Canada. But this particular track would miss us here in Northwest Ohio, but Alberta clippers do take more southerly tracks. And if we find ourselves basically to the north of an Alberta clipper track here in Northwest Ohio, we can get a couple of inches of snow out of that. Look at Alberta, and you can see that although we have lows that originate over Canada, that these lows basically originate over land masses, so they don't have a lot of water to play with. Alberta clippers are typically moisture starved, and so they are able to actually put down a strip of moderate snow just to the north of the low track, so you can get a 2 to 4 or 3 to 5 inch storm out of this, but not a big one. So if we get Alberta clippers that move basically for us in Bowling Green, you may literally want this clipper to be moving over Findlay. And in that case, you might be able to see a 3 to 5, 4 to 6 inch snowfall here in BG. Colorado storm tracks, these are storm tracks that are least side cyclogenesis storm tracks that form during the winter time. And so if the Colorado low actually cuts far enough to the south before it makes its turn to the northeast, we can again find ourselves in a favorable position here in BG to get heavy snow. But that's about it. It's really difficult here. The favored storm tracks actually take lows through the western lakes or the east coast when you're talking about the eastern half of the United States. And here's a classic winter storm surface map. And this is from Monday, November 26, 2018. You can see a low that's just beginning to occlude that's centered along the Illinois-Indiana border. And if you look really closely at Chicago, which is right here, you'll see that in Chicago, the conditions are occluded, moderate snow, winds at 35 or 40 knots. And so here in Chicago, it's just basically pouring down snow in a blizzard situation. So if you look a bit further to the east, in Detroit, actually this is just a little bit to the east of Toledo, you can see the temperature is much, much warmer at about 42 degrees. And so as this low probably is moving off to the northeast, basically here in Bowling Green, what will happen is we'll end up in the warm sector and maybe get some frozen or freezing precipitation that switches over to rain just before the occluded front sweeps through. So the heavy stripe of snow would be to the north and the west of us here in Northwest Ohio. Very, very classic winter pattern, a typical pattern where we miss out on the snow here in Northwest Ohio. Let's talk about this storm a little bit more. So what I'm going to do is I'm going to take a look at this storm in a couple of different ways. So obviously here's the surface map and the low situation with the fronts. If we take a look at 500 millibars and the surface, I'm going to actually talk about the thicknesses now. 500 millibar thicknesses. Now, this is something we've not really talked about yet in our class. Think about 500 millibar heights. 500 millibar heights is basically the height of the atmospheric column from sea level to 500 millibars, from sea level to 500 millibars. And as I talked about many times, the height of the 500 millibar surface is proportional to the mean temperature of the column between sea level and 500 millibars. What I'm going to do now is I'm going to define a different field that's just slightly different than the 500 millibar height. And this is the 1,000 to 500 millibar thickness. And so what we're doing now is we're taking a look at the thickness of a column between 1,000 millibars and 500 millibars. So the bottom of the column is always going to be at 1,000 millibars versus sea level. Lots of times sea level pressure is higher than 1,000 millibars, and occasionally it falls below 1,000 millibars. Now we're talking about a very specific boundary at the bottom of 1,000 millibars. So the 500 to 1,000 millibar thickness, again, its thickness is proportional to the mean temperature of the column. But because we always know what the top and the bottom pressure values are for this thickness, we can actually relate it to the mean temperature of the layer much more specifically. And you're going to do this in your exercise this week. So what we typically look at in meteorology, what we look at as a transition between rain and snow is the 540 decimeter thickness. So again, we're talking about thickness between 1,000 and 500 millibars. So 540 decimeters basically is the thickness that will tell us that snow will be able to basically make it down to the surface as snow. And in fact, statistically speaking, it defines the 50-50 odds, the 50-50 odds of demarcating between rain and snow. Now what you'll see, and you're going to do this in your exercise, when you calculate the average temperature of the 1,000 to 500 millibar thickness layer, you're going to find that's actually well below 32 degrees Fahrenheit or 0 degrees Celsius. That is because if we're talking about just the boundary between rain and snow, temperatures at the surface are going to be pretty close to 0 degrees Celsius. But that means that temperatures above the surface are probably going to fall well below 0 degrees Celsius. And so 540 decimeters, it is a basic boundary between rain and snow that meteorologists use. Now I want to note that because this is a 50-50 line, it's by far from perfect. It is not perfect. So this is just a first cut that meteorologists use. When meteorologists really want to make sure that snow can make it down to the surface, we'll typically also look at thicknesses and temperatures of lower pressure levels, 700 millibars, 850 millibars, 925 millibars, to really ensure that the column stays cold enough all the way down to the surface for snow to reach it to the surface. So you should think about this 540 decimeter thickness between 1,000 and 500 millibars as a first cut, just as an approximation. You don't want to take this measure and try and take it to the bank, particularly if you're going to be on TV, because you're going to make some big mistakes. You will see examples where snow can reach the ground in situations where the thickness is much higher than 540 decimeters. You can actually see it. I've actually seen it in the southeast for thicknesses sometimes as high as 552 decimeters, indicating a much warmer column. So what you see in this case is that even though the temperature near the surface is still close to 0 degrees Celsius, what you see is that temperatures don't decrease as rapidly with height in these situations. Okay, so that's all I want to say right now about the 1,000 to 500 millibar thickness and 540 decimeters. But on this map, this first blue line is the 540 decimeter line for thicknesses. Everything to the south of it is red, indicating that it's warmer and more likely to rain. Everything to the north of it is blue and colder, indicating that these thicknesses are more supportive of snow. All right, so when we're also talking about these big mid-latitude cyclones, obviously vorticity is an important consideration. So we keep coming back to chapter 12. So if you take a look at the setup, even though northwest Illinois is where the heavy snow is falling, remember that this is a cutoff low kind of situation. And in this case, what we see is that the surface low was located right beneath the vortex. And so even though this surface low is really strong at this point, note that on the map a couple of slides ago, it's also occluding. And so we have a triple point between our occlusion, our warm and our cold fronts to the south and the east. And what you see is that we have very strong shear vorticity in this area right here. And we also have decreasing absolute vorticity as wind blows through this wave pattern. And so you would expect for low pressure to redevelop just to the south and east of where the surface low is located. So the primary is right where the vortex is. You would expect the secondary to eventually develop to the south and east, where you have strong shear vorticity and you also have strong absolute vorticity that is decreasing. So everything comes together in terms of low movement, basically to the east of where the low is located at this time. If you take a look at the upper troposphere, so this is the 300 millibar height and wind pattern. Here's a jet streak, which is located over southernmost Indiana, right over the Ohio River. And where the surface low is located along the Illinois-Indiana border, what you see is that this low is basically just where the shear vortex is. But further to the east, where you would expect additional development later on, given our previous slide, you can see that this area is actually beneath the left exit region, where you get negative shear vorticity changes. So you get decreasing shear vorticity and you remove mass due to divergence in the left exit region. So basically, just to the east of the surface low, this is where you would have decreasing absolute vorticity at 500 millibars, you would have positive shear vorticity at 500 millibars, and you'd be beneath the left exit region of the jet core of this jet streak at 300 millibars. In better words, you would be removing mass from the column all the way up, which would really lead to strengthening low pressure over perhaps eastern Indiana and western Ohio. Now let's move on, because what I did in these previous slides, just to remind you, is that I've not actually added any new information. What I've done here after talking about thicknesses is I've really just put the pieces together from chapters 12 and 13. All of these details were discussed in chapters 12 and 13 in the YouTube videos for these chapters. And so while we only have 1 week, or I should say 1 chapter for week 6 of our distance course, you do have the opportunity now with our slightly reduced workload for this last week to maybe go back and review some of those earlier chapters, which you're still obviously going to have to know for the final exam. But you can just see the pieces coming together here. Now what I want to discuss next is a regional snow index that the National Weather Service has begun to use just during the past couple of decades. The National Weather Service is really fond of these indices that have levels basically 1 through 5. And so the Regional Snow Index, or the RSI, is an index that basically is developed to look at both, I shouldn't say both, there are 3 considerations here. Excuse me. It looks at snowfall amount, and that's an obvious one. It also looks at the aerial coverage of big storms, how much real estate is affected by a big storm, and then the number of people that are impacted. So here's an example of the Regional Snow Index for the March 12th to the 14th, 1993 blizzard that hit the eastern United States. Now, I think probably just about everybody in our class was born after this event occurred, but I remember it really well because I'm old, although I wasn't so old back then, so it was 30 years ago. And this was called the storm of the century at the time, and this really was an amazing snowstorm. So at the time, and this was about 4 years before I moved to Bowling Green, I was a research scientist up here in Albany, New York, and I was home for this particular blizzard here in Albany, and we got, and this unfortunately got on the Saturday, so it actually didn't close down any things for this day, and it was extremely well forecast. But in Albany, it basically started snowing right about dawn on this Saturday, and it snowed right through the evening into the overnight hours, and during that 18-hour period or so, we got 30 inches of snow. And if you take a look, you'll see a number of dots here where we had 30 plus inches of snow. And you can see that even down into a lot of Alabama really got crippled by this storm because they don't have snow removal equipment like we do here in the north. And some parts of Alabama received 18 to 20 inches of snow from this thing. After the storm ended and pulled off, the northerly flow behind the storm actually caused lake effect to occur. And Syracuse, which is right about here, Syracuse ended up getting close to 4 feet of snow between the main system and the lake effect when you put it all together. So it really was an historic storm that impacted a huge number of people, and it also impacted an extremely large area. So this was a Category 5, top category for this storm. Another big Category 5 storm, and again, this is amount plus area plus population, that's the main consideration. So this basically gives you the descriptions, and they're kind of vague, but notable, significant, major, crippling, extreme. Now, unlike tornadoes and hurricanes, the great thing about a big snowstorm is that if you just stay indoors and use your common sense, you're likely to just enjoy the event and get snowed in for a couple of days. So it's a lot different than hurricanes and tornadoes, which we also give categories 1 through 5 to. So most times what we see here is that when people find themselves getting in trouble with these big snowstorms, it's either because they get up, they go out in traffic, and they get caught in snow and get caught in their car, which obviously can be deadly, or they go out and they try and shovel this thing away when they're not in the physical shape to do it, and then bad things happen in terms of people's health. But other than that, if you just stay inside and use your common sense, these storms really don't pose much of a threat to people. Here's another example of a Category 5 storm. This one hit the Ohio Valley and the Mid-Atlantic, and this was from January 6th through 8th of 1996. And in this case, you can see a lot of areas with 30 plus inches in West Virginia, Northern Virginia, and all the way through southern Pennsylvania. And so this one actually missed New England and upstate New York. And if you take a look at both of these images, you will see that here in Northwest Ohio, and this kind of just illustrates my point, that even with the really biggest storms, we tend to miss out here in Northwest Ohio. So with the storm of the century, Northwest Ohio maybe got an inch or two. And with the storm in 1996 that gave so much snow to the Mid-Atlantic, here in Northwest Ohio, we didn't get anything. So it's kind of frustrating if you like snow so close and yet so far away. You can see, obviously, just to the east of Bowling Green, heading towards Cleveland and Northeast Ohio, a lot of these places in the second storm got 4 to 10 inches, and with the storm of the century, a lot of places in Northeast Ohio got 4 to 10, and even in extreme Northeast Ohio, 10 to 20, while again here in the Northwest, we just miss out. And so maybe you can hear the frustration in my voice. Okay, I'm going to move on and talk about another type of phenomenon that we see with winter storms, and these are for winter storms that impact the East Coast. And so what we see during the wintertime is that there's actually a climatological maximum of very large and powerful low pressure systems that develop along the East Coast, somewhere along the Carolinas, and then they move up along the East Coast through New England and put down a lot of snow on their north and west side. These are called nor'easters, and in fact the Appalachian Mountains have a really, really important role to play when it comes to East Coast snowstorms. So if we take a look at terrain here on the left-hand map, what we tend to see when we get big storms that form along the East Coast is that we get high pressure that is either located, centered over New England or southern Canada. And what happens is the clockwise circulation around the high basically pushes cold air down the East Coast. And as this cold air circles around the high, it comes into contact with the Appalachian Mountains. And this cold air, which tends to be fairly shallow because of its large density, its high density, this cold air simply is not able to make it across the mountains. It's not able to cross the mountains. And so as the cold air that's circulating around the high hits the mountains, what happens is it's funneled down the east side of the mountain since it can't actually cross the mountains. And we get something called cold air damming. So cold air basically dams up against the east side of the Appalachians, and then it basically funnels down the east side. So when we get cold air damming, what we tend to see is cold air that actually seeps or basically pours its way down the East Coast, while further to the west, even though it's further north, like here in Ohio, temperatures tend to be warmer. So here's an example of a cold air damming setup, and we have high pressure over Quebec, and the clockwise and outward directed circulation of the high pressure basically is pushing cold air against the mountains, against the Appalachians, which then basically dams the cold air, which then flows to the south along the east spine of the mountains. And so what this dashed blue line is the 32-degree isotherm. And you can see the 32-degree isotherm dips all the way into northeast Georgia, while all of these areas in Tennessee, Kentucky, Indiana, Ohio, and even the southern half of Michigan are warmer than 32 degrees because this cold air simply is not able to cross the Appalachian Mountains. And so what you see is a situation where we get low pressure developing along the deep south, we get overrunning to the north of the warm front, and then in this region of cold air damming where the temperature is below 32 degrees, we tend to see a lot of sleet and freezing rain. So we tend to get really big ice storms in areas that experience cold air damming before the low reforms along the East Coast and then moves up the East Coast and then pours a lot of snow down further to the north. So here's an example of a cold air damming event from December 15th of 2005. We have low pressure centered over southeast Alabama. Here's the low right here. You can see a short occlusion, so the low is just beginning to occlude, and then a very long warm front that extends through southern Georgia, and then the coastal Carolinas. And if you take a look at the station models, what you'll see is a number of locations where we have freezing rain in the upstate of South Carolina and southern North Carolina, the mountains of North Carolina, all the way into the Piedmont and into Virginia, before we begin to see a little bit of snow beginning to fall out of these clouds. And here's some sleet right along the Maryland-Pennsylvania border. And so you can see rain, freezing rain, sleet. These question marks typically refer to freezing rain. You'll see a couple of question marks. I'm looking for one or two of them. Here's one right here in southern West Virginia. So here's a question mark. That's almost always sleet or freezing rain. And if you just go to the west of the Appalachians, into Kentucky, into Tennessee, you'll see the temperatures actually go above freezing, even low 40s, and you'll see that we get just plain rain. And then further to the north, in northern Ohio, you can see, at least to begin with, we have snow falling out of these clouds, 32 degrees, and snow. When we get a setup like this, where we have cold air damming, I just want you to notice the isobars. What you'll see is that the isobars to the south of the high basically bulge down towards the south. This is a real classic signature of cold air damming. So if you take a look at our hypothetical here on the previous slide, you'll see the isobars basically moving their way down along the east coast. So we get this cold air damming, and we have this kinking of the isobars, and this is basically an inverted ridge, as we have ridging occurring to the south and the east of the Appalachians, which is basically a reflection of the cold air that's moving in this direction. And for this particular ice storm, here is kind of a post-mortem from the National Weather Service from Greenville, Spartanburg. As you can see, ice accumulations are color-coded right here. So freezing rain less than 1/8 of an inch is gray, all the way to freezing rain greater than 3/4 of an inch in the pink right here. And these ones indicate a couple of locations in the upstate of South Carolina and far southern North Carolina where an inch of freezing rain was measured. And just to put it in perspective, while an inch doesn't seem like a lot, an inch that basically accumulates on every branch and limb of a tree will bring a tree down pretty easily. And an inch of ice on power lines, again, that cumulative weight is more than enough to bring down power lines. So when you get 3/4 of an inch of ice, it is going to do a lot of damage, and it's going to put a lot of people into the dark. Now, the Appalachian Mountains are also really important when it comes to lake effect. So terrain also plays a role in lake effect snow, which is a big part of our winter climate here in Ohio, at least in the eastern part of the state and the northeast in particular. So the Appalachians are really important when it comes to lake effect snow, not because they trigger the formation of low pressure, but because they basically provide a lift mechanism for air that is coming off of the Great Lakes. So it doesn't matter whether you're talking about convection in a thunderstorm or whether you're talking about overrunning in a large low pressure system to the north of a warm front, you always are looking for some sort of a lifting mechanism for the air to give us lift and cooling of air inside a parcel to cool it to saturation so we can get clouds and precipitation. So terrain is really important when it comes to lake effect snow. Now, this is, again, terrain for the eastern part of the country, so we're focusing on the Appalachians. But if you go a little bit further to the west, so you take a look at eastern Ohio, obviously we're hilly in the eastern part of the state, not nearly as hilly as we are in Pennsylvania, New York, and along the spine of the Appalachians, but it doesn't take a lot when you have air coming off the lakes to actually provide that extra little bit of lift that will give us clouds and precipitation. So let's see what happens when we get heavy snow as a result of lake effect. Typically what will happen is we'll have very cold air that's flowing across the lakes. This air is typically cold and dry. So we're talking about very stable air. We don't get a lot of instability during the winter time. So this is cold, dry air that's flowing over the lakes. And what the lakes do, what the impact that the lakes have, first of all, is to warm the air as it flows over the lakes. Now, as the air warms, what you're doing is you're actually increasing the environmental lapse rate. And so the lakes can actually destabilize air that's flowing over it. And if the air lake temperature difference is big enough, you will get a large enough environmental lapse rate so that the air will become unstable and you'll get convection. So the lakes actually provide a heat source that can cause convection to occur over the lake, and then this convective air then moves over the land off the lake. But not only can you get convection over the lake, but because the lake is warming the air above it, the saturation vapor pressure or mixing ratio, we cover both of these in Geography 1250 and 1260, increases. In better words, the capacity of this warmed air to have water vapor in it increases exponentially. So the air warms, it becomes unstable, and we typically get a tremendous amount of evaporation into this air, which also leads to cloud and precipitation development as this rising air reaches the lifting condensation level, and in more extreme cases, the level of free convection, where we can actually get thunderstorm activity in lake effect. Now, as this rising air exits the lakes, and so the blue arrows, by the way, indicate the wind direction. So as this rising air exits the lakes, not only is it unstable, but it encounters terrain. And so the terrain provides another lifting mechanism for this air as it comes off the lakes and enhances the clouds and the snowfall. And so you can imagine that if this air is unstable, but it's not quite unstable enough for the air to rise to the level of free convection, the air, when it encounters the terrain, may actually get enough of an upward push for the air to then make it to the level of free convection and for us to get much more convective and heavy precipitation downwind of the lake. And that happens a lot with lake effect snow during the winter months, during the autumn actually, winter months, once it's cold enough for it to snow. And so we don't see the heaviest lake effect in the world here in Northeast Ohio. For example, Chardon is probably just about the location in Geauga County where we have our heaviest lake effect on average in Ohio. And Chardon averages just a touch below 100 inches a year. But we'll see places in Northwest Pennsylvania and Western New York in particular, Western and Central New York, that actually experience far greater amounts of snow than Chardon because the terrain is much greater. So we'll talk about that in a little bit. So we typically get two types of lake effect snow here in Ohio and in the eastern United States. The first type is called multi-band lake effect. So multi-band lake effect, as you can see here, we have these cellular rolls, and these cellular rolls are caused by convection. So what happens is you'll get convection along a line where you get rising air, and then what happens is you have on the sides, you'll get sinking air. So what you'll see with multi-band lake effect events is you'll get these streamers of convective cloudiness beneath which it snows extremely heavily, and then on either side of these narrow streamers, the sky will actually be clear. You can actually have sunshine that's actually occurring. So with multi-band lake effect, you basically go from heavy snow to clear skies, to heavy snow to clear skies, and so on. And so when we get multi-band lake effect, this typically occurs when the winds are blowing perpendicular to the long axis of the lake. So think about Lake Erie, where on the western end we have Toledo, and on the eastern end you have Buffalo. So if you just drew a line that connected Toledo and Buffalo across Lake Erie, that's the long axis of Lake Erie. We get multi-band lake effect off Lake Erie when the winds are out of the northwest and they're perpendicular to that long axis of the lake. So this is typically when we see this kind of lake effect. Now, if you're driving on Interstate 90 during a multi-band event, and you're on the turnpike or on I-90, what will happen is as you're driving, you will drive into extremely heavy snow for a couple of miles where everything is kind of really crawling along, and then all of a sudden the skies will clear and you'll be in sunshine for a while. And then you'll drive into another band where it's the exact same thing, maybe even whiteout conditions for a couple of miles, and then you're back in the sun again. So the weather is extremely changeable when you have a multi-band lake effect event. And these next slides are just a couple of examples of what multiband looks like on visible satellite imagery. So in this case, you can actually kind of get the direction of the wind just from looking at the streamers. And the streamers look really ragged. It's almost like an old rag mop. That's kind of what it looks like. But here are the streamers. They're really, really obvious. You can see the clear skies between the streamers. And you can see that even in smaller lakes. So I'm not even quite sure how to pronounce this. I think it's Lake Nipigon in Canada, you can see streamers coming off of this much smaller lake. And in fact, you don't need really large bodies of water to get lake effect. I've seen lake effect form on the Finger Lakes in New York and on Lake Champlain in Vermont. So the lakes can be actually pretty small to get lake effect. Now the winds here, if you just follow the streamers around, you can see that the winds are pretty much out of the north and the northwest. And if you take a look at where the winds originate over land, over Canada, you can see that there's no snow, no streamers. You have to have the lakes. Then as the air flows over the lakes, it takes a little while for this air to be conditioned from beneath by the lakes. It takes a little bit of time for this air as it moves over the lakes to be warmed. and for sufficient vapor to be added via evaporation to get the upward motion that will actually give us condensation and these streamers. So what is really important here, and I just want to point this out, are a couple of different factors. The first one is residence time. So the air actually needs to actually reside over the lake for a while to be warmed and have water vapor added to it via evaporation. So it's residence time as well as wind speed. If the wind is blowing very, very strongly, even though the air is over the same amount of lake, it doesn't reside as long, and you won't get as strong a lake response. And so residence time, wind speed, and obviously wind direction for this multi-band event really matter. So here's Lake Nepegon, Lake Superior, Lake Michigan is down here. You can kind of see the Lake Superior lake effect begins to wane as you move further away from the lake, and then it recharges as soon as it crosses Lake Michigan. So you can see the entire event beginning to flare up again, and new multiple bands getting ready to come off of Lake Michigan onto western Michigan. Here's an even more dramatic example of lake effect, again crossing Lake Superior, Lake Michigan, Lake Huron, and you can even see Lake Erie down here. So this is a day that's extremely unstable, where the lakes are really, really impacting the situation. And even here in Northwest Ohio, we're getting streamers making it all the way to where we live. So even in Bowling Green on this day, I imagine we had at least snow flurries falling from the sky. But even with this event, where we have such a strong lake response, you can see that the entire thing begins with strong, dry, cold air crossing the lakes, and the lakes still conditioning the air before we get the clouds and the streamers. So you can see we get dry air beginning over Lake Superior, we get a period of dryness over Lake Michigan before we can recharge the air and get our lake effect. Now, the other type of lake effect is a single or a dominant band lake effect event. And you can see that on radar, this looks very, very different than multiband. So what we have now is a single band, in this case coming off of Lake Ontario. This square right here is the location of the Montague, New York National Weather Service Doppler radar. So this is just basically Doppler radar, base reflectivity, showing a single dominant band coming off of Lake Ontario. And you can see that the reflectivities here are upwards of 30-35 decibels. And for snow, that is extremely high, because snow has a very high air content, and so you tend, even with convective snow, you've got a couple of yellow dots in here, by the way. With convective snow, you typically do not see these really, really high reflectivities. Typically with the heaviest snow, where you're getting 2, 3, 4 inches an hour, you'll see reflectivities maybe in the 35 to 40 decibel range, and not any higher. This is about as high as you'll see a reflectivity with snow. And again, when you've got a reflectivity in the 35 to 40 decibel range, you're typically talking about snowfall rates of 3 to 5 inches an hour. So extremely, extremely heavy. You get single band lake effect events when you have winds that are actually blowing parallel to the long axis of the lake. And this happens a lot with Lake Superior, because we have a lot of westerly winds in our part of the world. So when you get cold westerly winds crossing the long axis of the lake, what will happen is that this air will come off the lake. It's had a long residence time because it's gone along the long axis of the lake. So you've had a lot of warming, a lot of water added via evaporation to the air, and you tend to get very convective snow. And so you tend to get convective snow over a big band, and you get a lot of snow. And then as the snow comes off of Lake Ontario in this case, it then encounters an area called the Tug Hill Plateau, which is located right here, and then goes into the western Adirondack Mountains, which are right here. And so you get a lot of terrain enhancement, which further intensifies the snowfall rates. With Lake Erie, we get single band snow when we get southwest winds following a cold occlusion that will go all the way up the long axis of Lake Erie and will empty out right on Buffalo. So Buffalo tends to get its really big snowstorms, again, multiple feet in an event, when it has strong southwest winds, cold winds coming right off the lake and emptying right into Buffalo. So these big single dominant band events are the big ones. These are the ones that can put down multiple feet of snow in a day. And we don't really get these here in Ohio, because Northeast Ohio is basically downwind of the long axis. So Northeast Ohio is basically perpendicular to the long axis. Here's a visible satellite image of a single band event. And so you can see it basically forming on the western edge of Lake Ontario, coming all the way across the lake and then emptying out here in New York. And to give you an idea, here are clouds. You can see the Finger Lakes right here. So just away from the band, the skies are clear, and the Adirondacks right here, clear as well. So here is our single band event. Now, you can get tremendous snowfall from these single band events. And so this is probably the last really huge event that has occurred east of Lake Ontario. And I tend to pay attention to areas east of Lake Ontario because your professor actually owns land right about here. I own about 40 acres of land in the northeast corner of this county. This is Oswego County in upstate New York. Oswego County is kind of the snow capital of New York, and in the northeast corner is where the heaviest snow falls. The Tokyo Plateau, which is a plateau that forces a lot of upward motion as you get these single bands coming off of Lake Ontario, is basically located where we have my cursor circling right here. And so this was actually a holiday event in 2017 that started on Christmas Eve and went through the 27th. And during this 3-day event, there are areas in northeast Oswego County, including where my land is, that got up to 6 feet of snow. That's feet. So we're talking about 72, 75 inches of snow in a 3-day period. So you can really, really get tremendous snow here. And you can see, even downwind of Lake Erie, because there was a period of time when the winds were out of the southwest, you can see areas that got 3 to 4 feet of snow just downwind of Lake Erie as well. So really, really incredible snowfall amounts. We don't see this kind of snowfall in Ohio. A lot of you are probably really happy we don't see this kind of snow in Ohio. But I actually bought the land in New York because I love to cross-country ski. And so this basically guarantees that whenever I go up there in the wintertime, there's going to be something for me to ski on. Here are some pictures of what it looks like after lake effect snow. So this is at the intersection of County Route 17 and 15 in Redfield, New York, which is about 3 miles from where my land is located. And on the same day, this is the snowbank that was located along the street in front of my land. And so these signs, these road signs in Oswego County, and particularly in Redfield, where this was taken, these signs are actually much higher up off the ground. The poles are much taller than they are here in Ohio because of this heavy snow. And so this snowbank was probably 10 to 12 feet high. And so on this particular day, when I skied my land, I had to park my car right along the edge of the snowbank, put my skis on, and then basically point my skis parallel to the road, to the snowbank, and then go up the snowbank sideways, and then lower myself onto the land so I could begin to ski. So it snowed like we don't see here in Ohio, and like I said, most of you are probably grateful about that fact. Just to give you an idea of the fact that lake effect does not have to be lake effect, we actually can get ocean effect snow as well, where we have cold air flowing off of New England onto the Atlantic Ocean and then getting terrain enhancement, in this case right along Cape Cod, which leads to ocean effect snow. Same phenomenon, same trigger. So again, you're warming the air from below and evaporating vapor into it. You're destabilizing the air. And then when you get a little bit of terrain uplift, you can get this snowfall. So here's a band of ocean effect snow basically over Cape Cod. I also want to indicate that the Great Lakes, while they are great sources of instability and lake effect snow during the wintertime, the Great Lakes actually have the opposite impact on air during the summertime. So during the summertime, when we get instability over land as a result of intense heating from the sun and convection, what happens when unstable air flows over the colder Great Lakes during the spring and summer months is that the air is actually cooled from below by the lakes. This decreases the environmental lapse rate, which stabilizes the atmosphere over the lakes. And so here's a really nice example of a day that's fairly unstable over the land, where we have a lot of convective cellular activity going on. But as the air flows over the Great Lakes, you can see that the Great Lakes basically just squash that instability because of the decreased environmental lapse rate. And so the air becomes stable and there's no cumulus development at all over the lakes. You also get this really cool impact where you can see the shadowing of the lakes. You can see the actual outline of the lakes several miles inland off of Lake Superior, in particular off of Lake Huron and Georgian Bay, right here, and less over Lake Erie and Lake Ontario. So this actually gives you the wind direction. So you can see on the northern lakes that we have winds that are basically coming out of the west and the northwest. They're actually pushing the stable air inland and actually stabilizing the air over the land really, really well and just basically pushing the whole cumulus field off to the east. So really, really nice illustration of how the Great Lakes stabilize the atmosphere during the summertime. Also note that we can also get sea breeze thunderstorms during the summertime as well as this breeze comes inland. So this is basically a lake breeze. It's the same thing as an ocean breeze or a sea breeze. And along the boundary, which acts like a cold front, you can also get thunderstorm activity. Although to be honest, I'm not seeing any in this particular visible satellite image. All right, I want to say just a couple of things about wind chill factor, wind chill effect. So wind chill, because you're going to need this, I believe, for your exercises, wind chill is a measure of apparent temperature. It's not real temperature. So wind chill is meant to indicate what the temperature of the air feels like on your exposed skin on a cold day when the wind is blowing. So what happens with wind chill is that when you're outside and it's cold, your skin is warmer than the air around it. So what the skin does is it heats the air around it. It forms a very shallow insulating layer of air that adheres to your skin. So if the air is calm, what happens is that your skin causes this very thin layer of warm air that adheres to your skin to just be attached to your exposed skin. And then your body is still losing energy through this little layer of air from your warm skin to the cold air on the other side of this thin, slightly warmed air. And so when the air is calm, for instance, if it's 20 degrees outside, the air feels like 20 degrees. We are still losing energy from our skin to the air because our bodies are warmer than the air. But in fact, that little thin layer of air that's insulating us makes it feel a little less brutal outside. So it feels the actual temperature when the winds are calm. So you can see here, when the air is calm and it's 20 degrees, it just feels like 20 degrees. Now, if the wind begins to blow, what the wind does when we have air that is skin that's exposed to the air, so just think about your face not being covered. What the wind does is it very quickly and very effectively strips away that little insulating layer of air that's against your face. And so now you have cold air right against your face. Not only that, but because the air against your face is colder, the rate at which we lose energy increases. And so the temperature feels colder than 20 degrees. So you can see if the wind just increases from calm to 5 miles an hour, the apparent or the wind chill temperature drops to 13 degrees. And then you can see, just sticking with 20 degrees, that as the wind speed increases, the wind chill temperature continues to decrease. Now what you'll notice is that the biggest changes in temperature, from the actual temperature to the wind chill temperature, the biggest changes occur at lighter wind speeds. And this is because it's easier for our face, or whatever skin is exposed, to reestablish that warm insulating layer at lower wind speeds. And so we tend to feel a bigger drop in apparent temperature for lower wind speeds. And so you can see that as the wind speed increases from calm to 5 miles per hour, the wind chill decreases by 7 degrees. From 5 to 10, it decreases by 4 degrees. From 10 to 15, 3 degrees, and so on. So surprisingly, even when the wind increases from 35 to 40 miles an hour, you can see the actual impact on the wind chill effect is not great. And that's because there's simply no more warm air against our skin to strip away. Given winds this strong, no matter how our face may try to establish this insulating layer, it's not going to be effective. So at very, very strong wind speeds, what we see is that the wind chill effect actually really decreases in terms of the rate of cooling. So it still feels much colder than the actual temperature, but the rate of cooling really decreases as wind speeds increase at high wind speeds. This particular graph, which is a National Weather Service wind chill chart, basically shows you frostbite times. So you can see for wind chills around 10 to 15 below zero, frostbite times are greater than 30 minutes. Now you can still get frostbite, obviously, but greater than 30 minutes, and you can get yourself to safety. For these values that are in the 20 to 30, 35 below, you're talking about 30 minutes or less. For wind chills that are in the minus 40s and minus 50s, you can be outside, and if any skin is exposed to the elements, you can get frostbite, and better is your flesh will freeze in 10 minutes or less. And then for these really brutal wind chills, which we really don't see here in Ohio ever, you might see them in northernmost Maine or northernmost Minnesota and North Dakota. These are situations where you can get frostbite in less than 5 minutes. And of course, this happens in Alaska during the wintertime with some regularity. I just want to say one last thing, because so many of you are pilots in our class or are trained to be pilots, and that is just to remind you during the wintertime that when you fly through clouds, the cloud temperatures are almost always below 32 degrees Fahrenheit. And although we don't talk about precipitation processes in our class, I cover the Bergeron process in detail in both 1250 and 1260. So we talk about the fact that during the cold season, clouds are cold clouds. In better words, the temperatures of the clouds are cold, and the clouds are composed primarily of supercooled water droplets. And so if you're to fly through a cloud during the wintertime, what you would see is that you'd get a lot of water actually freezing onto your wings. And this deforms the shape of your wings, which can really, really quickly cause you to lose lift. And so if you don't have some way to heat the wings or to have some sort of a mechanism that actually breaks the ice off the wings, this can be extremely dangerous. And so I've spoken to a lot of students over the years here in Bowling Green who are aviation majors, and I know that you're not allowed to fly our planes through clouds when the temperatures are below 32 degrees Fahrenheit. And this is why. So supercooled water droplets freezing onto wings and causing really big problems. Okay, so that is all I want to say about winter weather in this Chapter 16 YouTube video. This is our final YouTube video of the class, and so I hope these YouTube videos have helped you. I hope they've made a big difference, particularly for those of you who are taking this as a distance class, and this is the only way you get lectures such as it is for our class. So I hope it's made a big difference. For those of you who are taking this face-to-face, I typically allow you to see these videos just before exams to help you with your notes, so I hope these videos have helped you as well. Now, for those of you who are taking the class face-to-face, keep in mind that this lab assignment is not your lab assignment. You have to go to our Canvas site and take a look at the PowerPoint presentation on Canvas to see the actual assignment for your lab group. If you're taking this class distance, here is your final lab assignment for the summer session. Okay, that's all I want to say. Just one last thing for those summer students. Any questions at all, by all means, feel free to post your questions to the discussion board or ask me live during my office hours on Zoom during the week. But that's it, that's all. I'm going to end this video right now. I'll post it on YouTube, and I'll post an announcement to the class when it's ready for you to view.